Welcome to the 16th lecture from chapter number 7. We are studying VLSI design and we are going to finish chapter number 7 in one or two more lectures. Right, there will be one or two more lectures and then chapter 7 will be finished, and then we will be moving to chapter 8. Right, so activity coefficient, the second last topic we will study in this lecture, and this is the second last lecture of chapter number 7. Right, so activity coefficient is the probability that a gate transitions from logic 0 to logic 1 or vice versa. I mean from logic 1 to logic 0. So it's the joint probability. This means P0, if P0 is the probability that a certain given gate transitions from logic 1 to 0, and P1 is the probability that it transitions from 0 to 1. The product, assuming these two to be independent, their product is P0 times P1 is the activity coefficient alpha for a gate. Before this, in one of our earlier lectures, we have studied that dynamic power is C out VDD squared times F. We studied this expression. A more complete expression for dynamic power is when we multiply this whole with alpha. Alpha is the activity coefficient, the probability that a gate switches, and we already know that this dynamic power comes into play when a given gate transitions from logic 0 to logic 1 or from logic 1 to logic 0. It's not the static power. We studied one more power, BDC, that was the static power that comes into play when the gate is there static in either logic 0 state or in logic 1 state. This is the power dissipated when the gate switches, in short. So alpha is P0 times P1. In order to understand this alpha, the activity coefficient, let's solve an example. Let's suppose we have this NOR 2 and NAND 2 gates. These are the two tables we already know. And to compute alpha for NOR 2, first compute P0 for this gate. P0 is the probability that the output is logic 0. This means it would have transitioned from logic 1 to logic 0. So that is 3 over 4. Why 3 over 4? Because there are 4 possible combinations, and out of which 3 of them are 0. Therefore, this is 3 over 4. And this P1 is 1 over 4 because for only one of these 4 options we have 1 here. That is why this is 1 over 4. Right, so it's very simple, and alpha for NOR 2 is 3 over 4 times 1 over 4 because it is the product P0 times P1. So 3 over 4 times 1 over 4 is 3 over 16. Right, and a similar analysis can be performed for NAND 2, where we have out of 4 options, 3 of them are 1. Therefore, P1 is 3 over 4, and out of these 4 options, only 1 is 0. Therefore, 1 over 4. If you multiply these two, it also comes out to be 3 over 16. It's interesting, and we'll put that here in front of this whole in order to get a more complete expression for dynamic power. We can extend this analysis further for any gate, for any Boolean expression, in fact. For example, for our NAND 3, it's a homework. It's a homework for students. Draw a truth table for NAND 3. A, B, C are the inputs, 0, 0, 0, 0, 0, 1, and you'll keep on going unless you reach 1, 1, 1, and then NAND 3 would be A dot B dot C, the whole complemented. This would be 1, this would be 1, and finally this would be 0. So you are to compute alpha for NAND 3. This is your homework. You will complete this table and you will compute this alpha for NOR 2, not for NOR 2 but for NOR 3. This is your second homework, and you have to have two more homeworks. Alpha for exclusive OR 2 is also your homework, and you need to find alpha for exclusive OR, for exclusive for exclusive NOR 2. These are your homeworks. You can find the answers anywhere on the internet and in the book. Right, that's all for this small lecture. Thank you.